This is problem number 4 on the practice problems for test number 2. The depth of lava in feet around a small vent of a volcano is given by the function d of x equals 1000 over x minus 40, where x is the distance in feet from the center of the vent and x is bigger than or equal to 50. What is the volume of the lava in the ring around the vent between 50 and 100 feet away? You may use your calculator once you write down an integral. So in order to have some sense of what's happening here, I'd encourage you to start with a picture. So I'm going to go ahead and try to draw a picture of that function, the 1000 over x minus 40. So here are my two axes. We can maybe plug in a few numbers into this function just to get a sense of what's happening. So apparently the function only starts to exist when x is 50. So if you plug 50 into this function, 1000 over 50 minus 40 is equal to 100. Let's go ahead and plug in 60 just to pick a number that's a little bit bigger. And I'm going to end up plotting a few points here. So in this case, we get 1000 over 20, which is 50. And then I'll plug in one more number. This problem involves 100 feet away. So I'll just plug that in to get a sense of what's happening. This one turns out to be 16 2/3. So what's going on here? Well, we've got these different points. We know that if we are, so this won't be to scale, but if we're 50 feet away, then the height of the vent is 100. And if we're 60 feet away, then the height of the vent is a little bit, it's actually half. So we'll come way down here. It's only a height of 50. And then if you get out to 100 feet away, now the height of the vent is only 16 2/3. So it feels like this is just some decreasing function. Is it justified to basically connect the dots with some decreasing function? And I think it is, because this function right here, if we ignore the 1000 and we ignore the minus 40, it's basically 1 over x. And I know what 1 over x looks like. It's got two pieces. One piece is here. That's part of the piece that we just drew. The other piece would be down there. So I'm quite content to say that the graph we have here is reasonable. And then the idea here is that the depth of the volcano is given by these numbers. So if you are, for example, 50 feet from the center of the vent, then the depth of the volcano is 100 feet at that point. So the volcano is 100 feet tall when you're 50 feet away. Well, this is only one spot which is 50 feet away. But for example, there's another spot over here which is 50 feet away. And in fact, there's a whole ring of spots that are all 50 feet away. So I feel like this is a solid of revolution. I'm just going to go ahead and draw another copy of that green thing over here. And then I'll connect the dots and say that there's this whole string of points that are 50 feet away forming this circle. And then there are a whole string of points that are 100 feet away that are way back there and have a height of 16 2/3. So I feel like I have a good sense of what we're trying to do here. We've got this three-dimensional solid, and we're trying to find the volume of it. So we've translated a problem that maybe it wasn't clear that it was a solid of revolution, but by drawing a picture and really thinking about the description here, I think we've got a shape that we can find the volume of using our standard techniques. So the next thing I want to do is point out that this equation is of the form y equals something, 1000 over x minus 40. And if you have an equation of the form y equals, then you'd really like your slice to be vertical because you already know what y is. So I'm going to go ahead and draw a vertical slice. I'll say since equation is of the form y equals something, we prefer a vertical slice. Now, if you wish, you can use a horizontal slice. It means you'll need to solve that black equation for x, which is not the end of the world. And in fact, you might try as a challenge to do this problem again, but with a horizontal slice. And you better get the same answer. We're going to go ahead and do this with a vertical slice. So my vertical slice, I'll just draw a generic vertical slice right here. And the idea is we're going to take that vertical slice and swing it around the y-axis in this case. That's where the vent is. So we'll swing it all the way around to here. And what kind of a shape do we get? Let's see. So it comes this way and then goes behind and then comes this way and then behind. And the choices are disc, washer, and shell. And I'm really hoping that we can tell by looking at that picture that it is a shell. And even without a good picture in front of you, if you recognize that the slice here is parallel to the axis you're spinning around, automatically it's going to be a shell. So we'll make a note of that. And that kind of follows from here. Since the slice is parallel to the axis, we are using cylindrical shells. Okay, so now it's a matter of the nitty-gritty writing down the formula. So let's go ahead and just dive into our integral. So here's the pretty much the only thing that I know when I'm using cylindrical shells is that it's the integral of 2 pi r h and then d something. So let's start to apply that formula to this example. So we've got the integral 2 pi. You're welcome to bring that out in the front. Okay, let's look at the radius of this generic shell that we've drawn here. So the radius I will draw in blue. So the radius of this particular shell goes from right here to right there where the vent is. And what's a good name for that distance? Is it x or is it y? And it seems like if you're calling this point up here x comma y, then the radius, that horizontal blue line, is the x. That's what the x is. So the radius in this case is just plain old x. And now we want the height of that shell. So let's go back up here and talk about the height. So the height is in red. I'm going to highlight it in yellow. This thing right here is the height. What's a good name for that height? So a good name for this, is it x or is it y? Well, it's y. So it's perfectly legitimate to just put y right down here instead of the height. And then let's go ahead and put the d and then the right letter. So over here, d something. So in this case, thinking about the fact that this right here is our width, the width of our shell or the width of our slice. And would you call that a delta x or delta y? So hopefully we see that's a delta x, which means that when we translate it into integral language, it becomes a dx. And then we're going to put some limits on the integral. So we need some numbers here and here. And you imagine taking your slice and sweeping it left to right. So how much is x when the slice starts over here? Well, if you start the slice there, then x is 0. But you got to pay attention to the problem. It says, first of all, the formula is only valid when x is more than 50. And more specifically, we want to find the volume of the vent between 50 and 100 feet away. So those right there are the two numbers that we're going to put. Oops, we're going to put those two numbers in blue highlight, and then we're going to stick them on the integral sign, 50 to 100. And that means starting here and letting this slice sweep out 50 to 100. And remember, you don't need to also do, say, minus 50 to minus 100, because this one slice swings all the way around and takes care of the left-hand side. So 0 to 50 is what goes here. Nope, 50 to 100 is what goes here. Okay, so the last piece of this, and then we can use the calculator, is to get rid of one of these letters. I have x and I have y. That's no good. This is the letter that I want, so that means that I need to get rid of this y, and you just have to replace y with what the definition of y is. So y is that tall, and to be that tall, it means you were on that green curve, and if you're on that green curve, you satisfied this equation. So instead of y, we're just putting this guy right here, 1,000 over x minus 40. So we'll highlight this formula, ends up coming right down here because it replaces the y. And so this formula now is ready to go into the calculator or into the computer. And so you just type it in. I'll go ahead and write down the answer. So for this one, we get about 764,478. And what were the units here? Feet. And this is a volume. So cubic feet are the units for this. And it is actually possible to do this integral without technology. So if you are interested, you can ask me for a hint on how to do that, but give it a shot if you want. It is challenging, but it is possible without any technology. And then, like I mentioned up above, you might also just for practice, and this is good practice, instead of doing the vertical slice, maybe try a horizontal slice and just see if you can then take that thing and sweep it up and down. You'll come up with an integral that really looks nothing like the one that we've got here. For starters, it'll have y's instead of x's, but if you've done everything right, then whatever integral you get there, even though it looks completely different, will be the same 764,000 and change.